Okay, separating variables, I'm going to multiply by y, then multiply by dx, correct? Yeah? Okay. Now we're going to take the antiderivative of both sides. And a lot of times, instead of writing it again, I'll just put the antiderivative in this step, the integral. Let's see here, antiderivative of y would be what? 1/2 y squared. Equals. Okay, antiderivative of this. Actually, we need a u sub on this one, right? U equals 2x. Du equals 2 dx, therefore 1/2 du equals dx, right? Okay, then you'd have a 1/2 out in front. I'm just going to rewrite it. Take my time. E to the u du. And then the antiderivative over here would be 1/2 e to the u, right? Which would be e to the 2x. And then we'll put our plus c over here. We talked yesterday about the point at which you could plug in your known value, your known x and y. This is as good as any, I think. So let's plug in 0, 2. Okay, 2 is y, 0 is x, right? 1/2, we'll have 2 squared equals 1/2 e to the 2 times 0 plus c. So it looks like 4 divided by 2 would be 2. And that'd be 1/2 plus c. And then if I subtract a half, I get what, 3 halves or 1/2. So c equals 3 halves. All right, now let's take that c value, our differential, our function anyways, our equation. Plus 3 halves. Okay, now we have to solve for y, because it says then f of x equals, that means then y equals, right? Solve for y, multiply by 2 everywhere. That works out kind of nice. Multiply by 2, multiply by 2. Keep solving for y, and we get y equals plus or minus square root e to the 2x plus 3. Now, do you guys see a plus or minus e to the 2x plus 3 anywhere? However, they told us the function f of x, or y equals, is positive for all values of x, right? So that means we only need the positive value of this. So y equals square root e to the 2x plus 3. Our addition is commutative, so our answer will be D, right? Okay, a lot of good things happening in this problem. Number 1, separation of variables. Number 2, you're going to have a u sub. Okay, hopefully some of you guys are seeing that pattern on this e to the u problem. If it's like a 3x, it's going to be 1/3 e to the 3x, always for antiderivative. You should be able to see that pattern happening. We subbed in our known values at a pretty convenient spot before solving, helped us out a little bit. And then at the end, we solved for y and got our original function. The derivative of this would be this, right? Okay. Questions on this so far? All right, let's go on to number 7 then. If the slope of a curve is 4x cubed y and contains 0, 5, then its equation is, we have to interpret this a little bit. If the slope of a curve is, that means dy dx equals this, right? Okay, so let's start out by saying that. Dy dx equals 4x cubed y. Contains 0, 5, that would be an initial condition to help solve for c on our antiderivative. Then its equation is, at the end of the day, we want y equals something probably. I really don't look at the answer choices just yet. Every once in a while I'll peek at them and just see, okay, are they all on y equals? Well, this one's not, but I'm not going to exclude it just yet, just in case, right? Because this one and this one look awful familiar, or similar, I mean. These look kind of similar, and this one's different. You never know, okay? So let's separate variables. We're going to have to divide by y, multiply by dx. Okay, I think we're set up to take the antiderivative then. That's not too bad, I believe. Antiderivative of 1 over y is natural log absolute value y, I believe, equals this antiderivative, okay, x to the 4th divided by 4. Okay, just x to the 4th. And then plus c, I believe. Okay, let's plug in our known values. X is 0, y is 5. Okay, y is 5, so that means natural log. I'm going to change to red here. That means natural log of 5 equals 0 to the 4th plus c. So c equals natural log of 5. All right. And then our function then, and this is where we're going to learn something new today. Our function then will be natural log absolute value y equals x to the 4th plus natural log 5. All right, now we need to solve for y. That means we got to get y out of the natural log function. The only way to do that is to convert to an exponential, or you take or raise everything to the power of e on both sides, right? So it'll be e to this equals absolute value y, correct? Okay. Or what a lot of people say again is you raise both sides to the power of e. Okay. I like doing it this way because then it's already written out for me. Okay. E to the ln of y, e to the power of natural log y, absolute value y. Well, that's going to be absolute value y, right? Because e to the power of natural log undoes itself, right? They undo each other. Okay. Equals. Now, here we go. E to the x to the 4th plus natural log 5. Remember what we did yesterday? And we have a sum in the power. We can change that to the product of the bases. E to the 4x times e to the natural log 5. Using our power rules, right? Okay. Now, why would we want to do that? It's actually simpler doing this. You'll see in a second. Okay. Let's go up here. Absolute value y. We'll take care of that in a minute. All right. I'm gonna leave a little bit of space here intended. E to the x to the 4th power. Okay. Now, what is e to the natural log of 5? Just 5. And guess what? We put that 5 on front now. Now, when you're solving absolute values, do you remember how to do that? Y equals this stuff, or y equals the opposite of this stuff. You guys remember doing that? Because if I have, let's see if I have absolute value x equals 5. Well, x equals 5, or x equals the opposite of what's over here. It would be negative 5, right? Because you take the absolute value negative 5, that equals 5. Okay? So here's how we undo this absolute value. Y equals plus or minus 5e to the x to the 4th. Now, Mr. Bonley, which one is it, the positive or the negative version? Well, guys, which one's going to include this point? The positive one or the negative one? If we have a negative out in front, it's going to take that exponential and it's going to reflect it across the x-axis, right? And so all your heights will be negative. Well, this height is positive, so the actual solution to this differential equation would be the positive one. Sweet. Now, what happens is some people try and just take this and they'll find the derivative. Don't do that. Actually go backwards, okay? Because some of these problems might be set up where their derivatives might be this. Okay, so just be careful with that. How are you guys in this one? Yeah? Why can I drop the absolute value? All right, so what would that be? 3e sine x right here. Okay, not too bad, right? These are actually fairly advanced problems, guys, and they're not too bad. Okay, here we go. 9. If, or any other questions on number 8? Okay, number 9. If f prime equals 2f of x and f of 2 equals 1, so we have the point 2, 1, right? Sometimes I like to write that down just to remind myself x is 2, y is 1. Then f of x equals, oh my goodness. Instead of this, what could we write to help us out? To write things in a form in which we've been working with right now. Instead of write what? Yeah, this is dy dx, right? Let's do that. dy dx equals 2f of x. What can I write instead of that? What is f then? Y. Yeah, it's 2y. There we go. That's it. This problem is much easier to work with. Okay, so the trick behind this one is writing it in a form in which we can find the antiderivative of smoothly. Okay, I'm not bringing the 2 along. I'm leaving it here with dx. I'm bringing the y over here. Okay, so 1 over y dy equals 2 dx. Then let's find the antiderivative of both sides. There we go. Let's integrate to both sides. Natural log absolute value y equals, was that just 2x plus c? Then everything after that, it's the same. Plug in your known value, solve for your arbitrary constant. Mr. Bond, do I have to plug in my arbitrary constant here, or can I solve for y and then plug in my arbitrary constant? Either way works. Okay, you might have to do a little more simplification along the way, but either way works. I like to plug it in right away, most of the time. Okay, so natural log of 1, it's positive, so no absolute value needed, equals 2 times 2 plus c. What's natural log of 1? Should be quick. 1 or 0? E to what power is 1? 0. Subtract 4. C is negative 4. And then just move on from there. Okay, do I have to write the absolute value now when I write this function or this equation over again? Do I need to write natural log, then absolute value y equals 2x minus 4? Nope, because their heights are positive, right? So natural log y equals 2x minus 4. Exponentiate both sides means raise each side to the power of e. And then we get y equals, okay, in this situation, I'd probably leave it. I'd probably stop for 1 second, look at this, and be like, okay, how do the answers look? And then, well, they got it. Because in this situation, you're subtracting powers. That means you're dividing the bases, and that looks less simplified, I think. Alrighty. Can you guys work on number 10? See what we got? Okay, I think we can get to here pretty easily, right? Separate your variables, multiply by y, multiply by dx. Here we go. Integrate both sides. And this is what we got. Now this is where the conic section of algebra 2 just comes into play. You gotta be able to recognize some things. Do we have both x squared and y squared? Yep. So that gets rid of lines, right? How about parabolas? I get rid of parabolas? Yep, because only one of them would be x squared or y squared, right? Y squared would be like this, x squared would be like this, okay? Now, is it nice and neat, and how can we differentiate between these? Now, since we're left with circles, hyperbolas, and ellipses, their functions kind of look the same, don't they? And it's usually all the things with variables on one side and your constant on the other. Let's move the things with variables to the other side then. So I'm going to write it as y squared over 2, and that's going to be plus x squared minus x equals c then. Okay. Now we could complete the square over here, which you guys probably did as one of the advanced problems in your conic section. But let's see, would this be a circle? Why or why not? And completing the square would be changing the center of our ellipse, or hyperbola, or circle, right? But why would it not be a circle? The ratio of the y is different than the ratio of x, right? Goodbye, circle. Okay, so this is an elongated thing, so it's going to be an ellipse or a hyperbola. How can we tell the difference? Functions look the same except for one thing. Right here. These are both positive, right? If one of them was negative, it'd be a hyperbola. So it's got to be an ellipse. So we're doing problems giving an initial condition, just having fun, and all of a sudden this problem jumps out of the paper, slaps us in the face, and makes us pay attention a little bit. And so we had to go through some of those processes that we learned in Algebra 2 or pre-calc of differentiating between these different types of equations or graphs of equations. Go through that process just like I did. Get rid of lines. I got rid of circles, parabolas, and that's between these two. What's the difference? Hyperbolas has a subtraction sign in between one of them, right? Ellipses, both positive. Okay?